there we are. This is we're all back here. It's a course in medieval French literature, right? This is I got the right class. Okay. There's a certain reentry problem. I guess we have all this a minor reentry problem. The bad news is that the second day of reckoning is approaching, but the good news is at least it's not this week. Right? It's next week. So that's Thursday, March 31st. The two chapters, just chapters 5 and 6. It's exponential distribution, Poisson process, continuous time Markov chains. We kind of all doing just that stuff, none of the earlier stuff, so kind of focus. So we're going to be doing that. We've been doing we did some of chapter 5, some of chapter 6, back to 5. Now I'm going to go back to 6. So we're doing that. This sort of, this at least has a focused stuff. We're doing this not the infinite body of probability theory, but just these topics. So this is kind of a nice, this is actually the nicest topic in the sense that it's very sharply focused. And there's only a few topics. So it's kind of, it balances, the sharp focus balances the fact that the term fatigue sets in now. And you're trying to make it to the end of the term. So I think that the format, everything's the same as before. Okay, now I want today again, right? So what do I want to talk about today, right? I want to fall off the thing here. Okay, I want to talk about reversibility again. So I talk about a few examples that exploit reversibility. So in particular, this may be reversibility for continuous time Markov chains, and it's section 6.6. So that may be the notes. I think this will be the notes. Online notes will be this. So I'm going to talk about this section today. And so I guess that means if you, it's there, so it's in the book, and I'm going to follow that somewhat. Well, I'm going to do my own take on it, but it's there. Let me just remind you about, so we're doing continuous time chains. So let me just sort of remind you here we've got, the model is Q, and we've got alpha Q equals 0. And we're always thinking now, in this setting, irreducible. And so we're actually after the steady state distribution, and here's this alpha. And Ross uses P, as opposed to discrete time Markov chain pi equals pi p. And that's because we use different notation, because we could refer to the embedded discrete time chain for which pi is sitting here. So this alpha has the problem of alpha j equals pi j This is the semi-Markov process representation, where if we know the steady state distribution of the embedded discrete time chain, these are the probabilities of being in J, and then this is the mean holding time, the mean time spent in J. And so the alphas and the pi's are related to each other. And well, there would be a P here for this matrix, for this discrete time chain. Ross uses P also for these steady state. So I'm using alpha. I've been following that consistently, but it's different from Ross. So pretty much The model here, continuous time Markov chains, the model now is Q, which is that's the derivative d dt of P of t at t equals 0. That's where this comes from. It's the derivative of the transition matrix. We don't really know the transition matrix, but we know its derivative by assumption, and we solve this. So fundamentally, the model is Q, and we're after alpha. And the answer is this system of linear equations here, and so we're doing that. But with reversibility, we have extra structure. But I mean, at a high level, we've got a continuous time Markov chain specified by the rate matrix Q, and we're going to solve alpha Q equals 0. And when we have this extra structure, we're going to do it faster. And it's going to be easier. And there's going to be nice things to say. But that's, so we're in the domain where it's irreducible, and we know this system of equations has a unique solution, and we're going to find it and talk about it, what it is. So we're describing alpha. Okay. So I want to talk about, let me sort of lay out where I'm going. I want to talk about two models, fairly classic, and I'll just say what they are first. I want to talk about the Erlang loss model. It's a classic model of telecommunications. And this no extra waiting room. So I have this queuing model, but I've been using this notation: arrival process, service times, number of servers, extra waiting room. So the arrival process is Poisson with some parameter lambda. Service times are exponential with some parameter mu, and there's S servers, no extra waiting room. And in this case, it's stationary, not like last time. Like last Thursday before the break, I was actually talking about M of t, where it was time dependent. But now it's not that, it's stationary. So this is a standard thing. So in the non-stationary context, you're not doing this. What I was talking about in the last class, we were talking about how you could do, in the last class I was talking about mtg infinity, and this was time dependent, so you had a lambda of t. And you have non-homogeneous Poisson. And even with this general distribution, you could solve this. But this is a good reference point. Yeah?
One quick question.
Yeah.
Is there a general formula for finding Pij of t?
So if you want this. Yeah, so in fact what we have is, behind it is this matrix differential equation, which we talked about, which means that this would be the derivative at 0, but this would be, if you stick this in, you could solve for this. So you would, your general equation would be this, which doesn't help so much because that means, so this is an matrix exponential. Well, it's the same kind of definition as the regular exponential. You can represent it this way, but that's not too convenient. So you end up with a problem of calculating this, which Ross discusses in the book a little bit. But there's an issue about how to calculate this. So actually, you don't much calculate this. I mean, the standard thing is you never calculate this. You define Q as your model, and you solve this, and that's your steady state distribution, and that's, you work with the steady state distribution, and you don't do this. But you could do it, but it's not customarily.
So we generally don't care what the probability is going from one state to another time being. Is that the...
Yeah, the reason being is it's hard to answer, and maybe mostly you care. The standard view, so this is in opposition to what we discussed last class, the standard view is that you've got these stochastic models and you're describing the long-run steady state stationary behavior. That's a standard thing. You make up a queuing model, an inventory model, and you want to know what happens in the long run average. That's the standard answer that you want to provide. In other words, the book will be mostly most stochastic processes books are fundamentally doing that thing. So when you do these problems, the model here is P, but when you find pi, you're finding a long-run average. And that's sort of the routine thing to do. However, when we were discussing this, we had the whole story about the absorbing chains, which was transient. And I'm certain now here we don't have any discussion of that, paralleling that. There was the ergodic theory and the absorbing theory, and the half equally balanced. Here we're only talking about the ergodic steady state story. And you could do it, but it's sort of more advanced. It's getting harder. What I did last time about this model was an example of what you can do that's pretty easy for the time-dependent case. That actually is very relevant for staffing systems. I mean, real systems, you know, that you make queuing models, the arrival processes are not constant. The arrival rates are not constant. They vary wildly. So it's an issue. It's an issue. But here, when you think of chapters 5 and 6, mostly, well, there was this, but other than this, it's just steady state. So this. Okay. And when I'm thinking of these, well, not this one. So I'm now thinking, I want alpha. That's what I'm really after, the steady state. So if this is a queuing model, I have Q of t. In this case, Q of t is the number of busy servers at time t. Or it'd be the number of customers in the system, because there's no extra waiting room. So everybody in the system is in service. And then you want to say probability Q of t equals j. What happens? This goes to alpha j as t goes to infinity. And that's the thing we're solving, right? We're solving alpha q equals 0. So, okay, let's think about what that so a main exercise is here, what is Q? So Q equals what? And in this case, we recognize that we have a birth-death process. So that means we write Qi to I plus 1 equals lambda I, and Qi to I minus 1 equals mu I as definition. So we're just going to define the birth rates and the death rates. So this you can only go up or down one at a time, because everything's happening according to Poisson process and exponential, so events happen one at a time. So if there are k people in the system, you're going to go up one or down one. Or I people in the system, you're going to go up one or down one. And then you need to know those rates. So in this case, the birth rate is always lambda. There's an arrival rate lambda as long as I is less than or equal to s minus 1. Because if there are s there, no more will come in, because they'll be lost. There's no room for them. So it's 0 when I equals s. Now then, the output rate is just I mu. If you're in state I, there are I customers in the system. Each one is being served at rate mu. I mu will be the total rate out. And the birth-death, now, this is where the reversibility comes in. You can think of the birth-death as having I, you draw one of these diagrams like this, a state diagram, and then you have the rate this way is lambda I plus 1, and so forth, and then down this way is mu I plus 2, mu I plus 1, and you say, okay, well, let's alpha I lambda I equals alpha I plus 1 mu I plus 1. That's the stationary rate across this line, flow this way, and equals the stationary flow that way. Alpha I is the probability of being here, and lambda I is the rate of going this way. Alpha I plus 1 is here, probability of being here, and mu I plus 1 is the rate going down. And you can only cross this line from these states because you don't move 2 states at a time. So you just have this simple equation, and this is the reversibility equation. Okay, well, I'm just going to, was going to outline, but I'll just keep talking about this. The theorem that sits there in reversibility is, the reversibility equation in general is this. So for Q given, so for Q given, suppose you can satisfy this equation as it's occurring right here. This is true for all, this is true. In other words, if the states aren't next to each other, there's going to be 0. But this is the reversibility equation. That's just this equation here for all I and j, and this is only going to give us positive entries when j is I plus 1, when j is I plus 1 to I. So j is, well, j could be either I plus 1 or j is equal to I minus 1. And then either way, you're getting this, an equation of this form. You're either going up or down 1. But the general theorem is, for a continuous time Markov chain with a given Q, if you can find this for some alpha, that's it. Right? So if you can solve these simple things, that's the alpha you want. And all you have to do is just sum these things. It's just like the discrete time version. We did this same thing in discrete time before. It's in chapter 4, exactly the same stuff. It's just a continuous time analog of the discrete time. So it's the same thing. It's saying if you've got a Q matrix and you can solve this local balance equation, then you get this alpha. You don't need to solve an n by n system of equations or an infinite set of linear equations. You can just solve this thing, which you can do recursively. So it's easy to see that if you knew alpha 0, you could solve alpha 1 in terms of alpha 0, alpha 2 in terms of alpha 1, and so forth. So you can solve it recursively subject to some initial condition, and you get that initial condition by the condition that the probabilities all sum to 1, right? Probabilities all sum to 1. So in the end, you're going to be able to solve this thing, and you can just check that this is so by adding this thing up, and you'll produce this. So all the examples we're going to talk about are going to be this reversible structure. We're going to exploit this. That means we're not actually ever going to deal with this system of equations. We're going to have this kind of thing. And here we have that. Well, any birth and death process. So another theorem is any birth and death process has this kind of equation, and we'll have this solution. Now, in order to be reversible, this is the same thing as discrete time. A very important condition is that you have to be thinking of the process in equilibrium. You don't go the same. It's not the same going forwards and backwards unless you've got the stationary distribution. So this is the stationary. You're operating with the stationary distribution, and with the stationary distribution, if you're in I, this is the rate of flow to J, and this is the probability of being in J and the rate of flow to I. So you've got to be in equilibrium. Okay. Okay, what I want to do here, I guess in this model, is the solution to this model is a classic formula, Erlang-Loss model. This is used to size telephone trunk groups. It's sort of really classic model. And you can solve it by doing this recursion thing, which we just talked about. But it also has a simple form that's easy to know. The answer at a very high level is to use more of a reversibility to see structure. So I want to connect this to what we were doing last time. So last time we were working on this queue, infinite server queue, but I want to specialize that to this. So it's stationary Poisson arrival at a fixed rate lambda, exponential service with rate mu, but infinitely many servers. Now, if you'll remember here, in this model, the time-dependent distribution for every time, this is fantastic, the time-dependent distribution in this model is always Poisson for all times. But it's got a complicated formula. The mean is some complicated formula. Right? It's a little complicated. But the main thing is it's Poisson, which means that every time the distribution is characterized by a single parameter, just its mean. So what must be the distribution, the steady state distribution here? Also Poisson. This is simple. So as a consequence of all this, you see that in the infinite server model, the steady state distribution, actually the time-dependent distribution is like this also, will also be Poisson for this general theory. If you started off empty and you said, what's the time-dependent distribution? It'll always be Poisson. It'll have some complicated formula. This kind of stuff is in Ross in Chapter 5. This is in Chapter 5 is this infinite server Q, and as a special case will be this one here, and in this special case, the mean is just times the expected. It's the arrival rate times the mean service time. So then, with knowing this is what we talked about last time, and this is a special case, and so we know it's Poisson, and it has this mean, which is sort of the obvious thing that it ought to be. The expected number of customers in here obviously ought to be proportional to the arrival rate and ought to be proportional to the mean service time somehow. And it's directly proportional to this is 1 over mu, right? Mean service time, arrival rate. So it makes sense. If you doubled the arrival rate, the mean in the system is going to go up, and it's actually, everything's linear. So when you review this, you'll see this. Now the point then is how to think about this. Here is this. What I want you to do is think about, here we have an Erlang loss model. It's an S-server system with no extra waiting room, and what I want to do is relate that to this, infinite server. And the thing that's happening with this reversibility, I guess the one theme is, if you think about this in the right way, here's a thought, is if you can engage yourself to get into the problem and think, here's this thing, what would be the best answer I could imagine? Okay, you've got to engage yourself enough to say, yeah, I understand that model. What should the answer be if it was the simplest thing? The simplest thing you could think of that makes sense, right? And that requires that you actually, this is a mindset that's right here. So if not now, just keep this thought in mind later when you want to try to understand it. Because this stuff we're going through has the property, to some extent, that the best answer you could imagine is the right answer and comes out. Everything comes out perfectly. It's just like the exponential with the lack of memory. All that stuff's going on here. So all the good things happen. Yeah.
M is equal to lambda over, are you talking about the mean time?
Yeah, this is the mean. So this is, in terms of alpha, I'd solve alpha q equals 0, and then the m is, right? M is just the mean, steady state mean of alpha. Just the regular mean of the steady state distribution.
So in this case, why would it just be 1 over mu? Because if there's infinite number of servers, why does it, then wouldn't they go into service immediately?
Yeah, they go into service immediately. So this is, in this case, this alphas we're talking about is the number of busy servers or the number of customers in the system. There's nobody waiting. Nobody waiting. They all go into service immediately. So indeed, if anything, the part I'm missing, your question raises, is you need to understand the model before you can have any opinion about what's the right answer. So the model is, they arrive according to this Poisson process, and because there's infinitely many servers, they never have to wait. They go right into service, and their service times are exponential. So, and then they take 1 over mu as their expected time in service. So if you double the rate, there's going to be more there. So it's sort of, and if they take longer, they're going to stay longer. You know, the fact that it should be proportional to lambda and proportional to the mean, and the fact that they don't have to wait makes you realize it's linear and nice, because there's no congestion. They arrive, they start service, and they leave. And they're all independent of each other in the sense that Poisson arrivals sort of, if a Poisson, if you know an arrival occurred at t, it doesn't tell you anything about what happens anywhere else, because the Poisson property makes everything sort of independent of, even though customers come in a stream, they're independent of each other. So at any rate, this is the mean of the steady state distribution. It has this simple form. And the distribution is Poisson, and that's all part of this story. Now then, given we know this, suppose the rule here is we only have S servers, not infinitely many. So what happens here is the following thing. When there are S customers in the system already, a new arrival comes and just leaves and just goes away. Doesn't affect the future arrivals, doesn't affect anything, just doesn't get in, right? Just doesn't get in. So everything's going just like in this model. Arrivals, services, everything, except when you hit S, no new arrivals come. They just go away. So how should this alpha be related to this one? You know, what would be the best thing you could hope? Well, suppose, for example, to take a little orient, suppose S is really big or the arrival rate's really small. If S is really big, the answer ought to be sort of the same. Because it might never hit it. If S is really huge, the answer ought to be the same. Because it would make no difference, almost. Right? So in some sense, if it was big, it wouldn't make any difference. So the thought is here, if we think of, I guess I should not use Q, I should use X as the steady state, XS, steady state, and X, infinity. So this is the steady state number in here, and X infinity is the steady state number there. So you want to think probability XS equals K. Well, that better be for K less than or equal to S. How is that related to this is what I'm looking for? Sort of. I mean, this can't be right, right? This can't be right, because this has got to sum to 1 for these K, and this has got to, it's going to sum over all K all the way out. There's going to be positive probabilities everywhere. But I want these to be related somehow, so I want to clean this formula up. I'm thinking possibly my orientation to this problem is a little weird, and I'm not sure I'm on my own private wavelength. Okay, I'm sorry about that. Can't help it. Okay, so the thought is to relate this, and I guess what I want you to see is the simplest thing you could hope for might be this. Or in other words, here is this model with S servers. What you might think is the simplest thing is that the steady state distribution of the model with S servers is just the steady state distribution with infinitely many servers conditioned to be less than or equal to S. Which is just this, because when I intersect these two, I just get this, and then this is the number. So this is just the definition of conditional probability, that this, and this are equal. Now, needless to say, most of the time such a relationship is not true. I mean, if you take a multi-server queue and you take an infinite server queue and you say, well, what's the distribution? It's just going to be a truncation. This is just a truncation of this distribution, right? You truncate it and renormalize. All I do is take the infinite server distribution and truncate it at S and renormalize so it sums to 1. So I don't need to know anything new, right? I don't, if that's true. And so that tells you conceptually what this distribution is. I mean, one way to know this distribution is you solve alpha q equals 0, and you do it recursively. So you're doing this alpha I lambda I equals alpha I plus 1, and then in this case it would have been mu I plus 1, because that's the, in this model, this is this equation for this birth-death. So you know from one point of view I can just solve this and I'll get the answer. But this is giving the answer in another way that tells you what the answer is structurally. The steady-state distribution here, if given that this is true, it's the truncated Poisson distribution. That's what it is conceptually. So you say, well, the infinite server has a Poisson distribution with this mean. The loss model has the same distribution truncated at S. It's a truncated Poisson distribution. So it looks a little bizarre. This distribution, you'll see if it was this is the way you'd see it in the book. Yeah, just another formula to memorize, right? It's another formula to memorize, but you don't want, it doesn't look familiar. But of course, if you do this, this is the Poisson probability of k, Poisson probability of j, right? But these exponential terms in the Poisson are just constant, so they'll drop. These will cancel, right? So you see this thing in a book as something to memorize. Bunch of factorials, bunch of more nonsense to memorize, right? But conceptually, it's just the Poisson distribution truncated. It's the conditional Poisson distribution given that you're less than or equal to S. So that this thing has a very simple story. This structure tells you its steady-state distribution is the Poisson distribution, which is the infinite server result, truncated or conditioned to be less than or equal to S. And what is the theorem? So this is this Erlang distribution that goes with this. The theorem that'll sit there, if you take a reversible continuous time Markov chain with alpha and q, then and you truncate. Now, what this is going to mean, you're going to truncate to a state A, so you're going to get, let's call a steady state. Steady state is x. So the probability x equals k is equal to alpha k. So this is the random variable that has the steady state distribution. Then if you want to truncate to A, that means that you only allow transitions that take place within A. Everything has to take, it's some subset, but you're moving around in A and you can't get out and you just stay within A. And so the rates out of A don't happen. You sit in A. And then the thing you're going to get is the probability XA equals K equals the probability that X equals K, which is this is the conditional probability of this given that you're in A. In other words, when you truncate the process, you truncate the steady state distribution. And it's easy to see from the reversibility formula because this formula I This reversibility formula is going to be the same thing because you're going to have the rates, this rate thing. This thing is going to be truncated at the same constant, and these rates are the same as before wherever they're allowed. So if I put this to stand for the truncated ones, this equation, when you look at this reversibility equation, you see that truncating does not change that equation. So what's happening is if you take a reversible continuous time Markov chain and you truncate, it's again reversible. And its steady state distribution is just a truncation or a conditional distribution. So anytime you have a reversible thing and you truncate, boom, it's just the same thing. Which is easy to see because when you look at this equation, you see nothing changes. In other words, these probabilities change because they're a constant multiple, the same constant, so they cancel. These rates are the same or zero. So it's the same, it really becomes immediately the same equation. So this model just appears as a truncation of the infinite server model. So the simple, just things you know about larger things will apply to smaller things. Okay, now this truncation, the truncation that's taking place here is the same one here. This is a nice simple setting. It's one-dimensional. The state space was originally infinite. We truncate to 0s by just not letting transitions from s up happen. Now here, this is done very abstract because this could be 37-dimensional process. Very complicated, not just birth-death. Any reversible continuous time Markov chain, you truncate it, you still got the same thing, and you just solve the untruncated one and renormalize, which helps lots of things. So then, when you for example, if you now say, well, in this model, single server, we know that the steady state distribution is geometric, where rho is, we have this. You'll see the single server queue, x plus on arrival exponential service, one server, unlimited waiting room, geometric. When you go to R waiting spaces, you then have probability x r equals k equals probability x equals k, probability x less than, well, now I guess I should have 1 plus r, because I have 1 plus r spaces. Just this condition. So this is that geometric thing. This is if I write that down, that's this rho to the k times 1 minus rho over the sum of rho j from 0 to 1 plus r. And in this case, these cancel the same kind of way, and you see some formula that's you could also memorize. But I mean, this one, the infinite one is geometric. So like if you do the single server queue, you see the steady state distribution is very simple, it's geometric. If you do the infinite server one, it's very simple, it's Poisson. This truncation property tells you what all the other things are. All the other models that are just truncations of the previous one, finite state space, come in from this property. So this has some formula that looks like this. This looks another thing you could learn, but it's just the conditional distribution of a geometric. Okay. Well, the theme here is truncation. If you have a reversible process and you truncate the state space, the truncated process is again reversible. And its steady state distribution is a truncated version of the steady state distribution, and that enables you to solve lots of these problems. You have to have a burning desire to want to solve these problems to appreciate this point, which may or may not be there. Okay, so I want to now talk about We're still talking about reversibility, but I want to talk about another property which comes out of another situation. So I want to consider one Q and then another Q. So so you might think of, as we're beginning to think of the L word, we're beginning to think of lunch. So we're beginning to think of lunch. This is, we're thinking maybe if we didn't, especially if we didn't eat breakfast, we're thinking of having waffles for lunch. And this first station is the waffle station. And there are S1 eager servers here ready to prepare waffles for you. They're manning each of these waffle irons. And then after that, there's S2 servers ready to put all this great topping of all sorts of stuff on top of our waffles. And then you go, okay? So you got this waffles. And of course, being orderly or totally random, the customers arrive at a Poisson process at rate lambda. And there's, we'll let there be unlimited waiting space, but we assume the service times are exponential with mean. The mean would be 1 over, mean is 1 over mu1, and the mean here is 1 over mu2. So this model would be, if we did the notation, we might enlarge it this way. It's 2 stations, station 1, and then this is lambda, this is mu1, and this is mu2. So we have lambda, mu1, S1, mu2, S2. We have 1, 2, 5 parameters. And we assume everything inside is exponential to simplify everything. So we have the rate in, Poisson, the service rate, mu1, number of servers, S1, service rate, mu2, number of servers, S2. 5, just, they're actually all describing numbers or rates, right? There's nothing really stochastic. Everything, the stochastic part is always exponential. The inter-arrival times here are exponential. The service times here are exponential. The service times here are exponential. They're all independent by assumption to make everything simple. So the model is very stochastic, and yet it's all described in terms of these 5 deterministic parameters. They don't have anything directly to do with variability. All the variability has to do with the 3 exponential variables, the inter-arrival times and the 2 service times. Now we might want to know how this, how long, what's the expected amount of time it'll take you to, if you come here, what's the expected amount of time will it take you to get through here? Or, yeah, there we have it. What's the expected time it will take you to get through here? Or what's the distribution of the number of customers? You could have x1 and x2. This is the number of customers here and the number of customers here. So we might want probability x1 equals j, x2 equals k in steady, and this is steady state. Again, it sort of makes more sense to focus a little harder on the waffles. At this point, we could develop an interest in the waffles, but anyway, the thought is, well, here, looking at this model, you'll see that this is a continuous time Markov chain. You could solve alpha q equals 0. However, it's 2-dimensional, and in each dimension there are infinitely many states. So this is an infinite dimensional system of linear equations, and it's even 2-dimensional, right? Because the state space would be jk, j at the first station and k at the second station. But if we look at this, we move, you can see how you go from jk that you're going to go to, well, let's see, if you have an arrival, you're going to go to j plus 1k. If you have a service at the first station, you're going to go from j minus 1, k plus 1. And if you have a service at the second station, you're going to go to this, right? So the transitions from this state are these 3 that you could go to. This happens with an arrival. This happens with a service at the first station, and this happens a service at the second station. So these are the rates. So the row from the jk would be, this is a single element on the matrix Q, right? I mean, this is a, Q has to list the JK down this way, and so on here, because the state is the pair. But for the row corresponding to the state JK, there would be these three states you could go to. So, I mean, this matrix is huge, but this row will have three positive entries off diagonal plus the diagonal entry. So that's how you make the Q matrix. But we want to get, the point of going beyond just solving alpha Q equals 0 is we want to find the answer to this easily, in exploiting reversibility. Okay. And as time passes, our interest is increasing, and the waffles increases. But anyway, we're going to persevere for a few more minutes to think about how to get this. We'll get this out of view. This sort of suggests the general cleaning up of the board and stuff. It suggests that I perhaps forgot what to do next and how this proceeds, and that I'm hoping for divine inspiration. Okay? Well, yeah. Fortunately, the story is so good. Once you know it, you can't forget. So I'm not in trouble really here. The story is so good. So what would be the arrival rate here? Let's have some participation. This is not going to be too tough. What's the arrival rate here? Yeah.
That's one.
Okay. The floor opened up. You just fell into the alligator pit. You're in the alligator pit. Somebody that. But your answer is not unreasonable. One point would be, what would be this rate instantaneously? And instantaneously, if I know there are K customers here in service, say they're all in service, then it's going to be K mu 1, something like what you said. But I mean in the long run. So actually your question is good, although you're already in the alligator pit. But anyway, you're in the alligator pit. The point is, instantaneous rate depends on the state here. But long run rate. On the long run, what's the rate of arrivals to the second station? Somebody else has got to face the risk of falling into the alligator pit. Yeah. How hard was that, right? Okay, yeah. I mean, this is like who is buried in Grant's tomb. You got to be ready. You got to be ready, right? This is an unlimited waiting room. So unless there's something wrong here, I mean, unless this rate in is, it blows up. As long as lambda is less than S mu 1, the rate in is less than the maximum rate out, I need this, right? I'm in trouble if this is not true. But if the rate in is less than the maximum rate out, I'm going to get everything eventually coming out. And this will be lambda. And then, therefore, what will be the rate out here? Seven lambda? 2 lambda? Wait, lambda. Okay, lambda. Assuming that lambda is also less than this, right? We need these conditions. Rate in, it's got to be less than the maximum rate out. And these conditions are going to be needed for the steady state to exist. If the rate in is faster than the maximum rate out, obviously the thing's going to blow up. So alpha Q equals 0 will not have a solution then if these conditions are violated. But it's not too easy to see what that thing I got rid of it. The solve alpha Q equals 0 is hard to figure out. Okay, this part's supposed to be the easy part. Now, what's this arrival process to this next station? I mean, its rate is lambda. It's complicated because this arrival process comes out of this Q. So we don't want to, it depends, of course, if we start off empty and we're talking about the beginning. If there's nobody in here, then the arrival rate's essentially 0. So this is, I've got to think of this in equilibrium. The whole thing's in equilibrium, in which case I can think of it as positively. That's important. So I want the system in equilibrium. So there's a steady state distribution of number of people here. And somehow, sometimes it's empty, sometimes they're all busy, sometimes there's a queue, some steady state distribution here. So then there's some kind of process coming out here. This is Poisson here, and it goes through this queue, and some mess happens, and it comes out here. So the thought is, what would this be? What would you want it to be? Well, maybe the best thing of all would be that it was deterministic, right? Now it's maybe this is constant now, but not too believable, right? Because this thing's all random. So the thought is, what would this be as a process? What would we want? What would be the easiest thing to have it be? Right? The obviously answer, even though it goes through this mess, that this would be Poisson. Surely this is not going to be independent of this, because the state here is going to determine what this is. And yet, if I just forget this and think, what is the arrival rate here? Well, it's not so clear that, okay, so this, now it might actually be even more than that this might be Poisson and this might be independent of this. How many is here? So we could think of x of t, x1 of t, that's how many are here in steady state. So an ideal thing would be that this is Poisson and independent of this, which would mean this is going to be independent of that. But that seems really unbelievable. This would be Poisson just like that, and the output process would be independent of what's in here. Okay, so here's the thing I want you to do is you just focus on this first Q of these two Qs in series. Just think of this one. Okay? Now, if you draw a picture sort of what happens, this is not supposed to be anything too subtle. Here's x1 of t. And I guess I'm recording here. I've recorded with these arrows the departures from this queue. But this is the sample path. It's an equilibrium. Boom, and up. Rivals going up, service completions going down. Thinking about this queue. So the thing you want to do here is you want to remember the whole point of this, the whole talk, today's rant is that we're focusing on reversibility. So reversibility means that the system is also this model in reverse. So if you go in reverse time, consider this system in reverse time. That reverse time means you're going to go this way. So in reverse time, these departures in forward time become arrivals, and the arrivals become departures. So the system in reverse time is the same as the system in forward time, same distribution as a system. It's reversible, behaves the same backwards as forward. When you go backwards, arrivals become departures and departures become arrivals. So now consider what happens forward. Forward, by assumption, this is a Poisson arrival process whose arrivals occur independently of the state. When we go in reverse, the departure process becomes an arrival process. So the departure process is going to be a Poisson process independent of the state by doing this reversibility. The reversibility is only occurring in equilibrium. That means this thing is not starting empty at something like that. This is always in steady state. And in steady state, going forward and backwards has the same distribution. So when we go backwards, we see that the departures are now like arrivals. So then we deduce that the departures are a Poisson process independent of the state at that time. So this departure process, the departures up to time t, are going to be independent of the state, which is just like here. The arrivals are independent. The arrivals are independent of the arrivals after time t are independent of the state up to time t, to be precise, right? The arrival process is operating independent of the system, but of course old arrivals will affect the state. So future arrivals are independent of the current state. And therefore, in the departures, future departures, past departures will be independent of the current state. So what you're ending up with this picture is this process is Poisson, and this is independent of this history here. So that in steady state, this Q is going to be independent of this one, its distribution. At any fixed time, these two Q's are going to be independent of each other, which isn't necessarily going to help you with your waffles any better, right? But you're now going to be able to answer this fairly easily. That's going to tell you that they're independent. This and this. And that this Q here is another one of these. So each of this one is an MMS1 Q, and this is an MMS2 Q, and this has lambda mu1, and this has lambda mu2. And each of these are separately birth-death processes, so you can use the standard steady state for these two separately. So the distribution of how many are at the two Q's in steady state at one instant is they're independent, and so it's the product of the probabilities, and each one separately is one of these simple queuing models. So that the complexity is greatly reduced. Well, let's just think this to echo this thing. Let's think a little bit more carefully about this independence, forward and backwards, because the arrivals. Let's see if we can make this, review this, and make it more convincing. If we look at the arrivals, arrivals, and then there's x1 of t. The arrivals after t, are independent of this state, because we assume that the arrival process, the Poisson process, is operating independently of the system, but the past arrivals determine the state, but the arrivals after t. So now when we go in reverse time, this becomes departures before t. So just thinking of, we're thinking of these arrivals. We look at some time, then these are, here's time t. Going the other way, these arrivals going up here will be in reverse time. These will be departures. So it's here's the arrivals, and here's x of t. It's future arrivals are independent of this state. Well, future arrivals are past departures going this way. So the arrivals after t are independent of x of 1 of t. This is by assumption. But by reversibility, this corresponds to the departures before t being independent of the state at t, which is the same distribution either way. So I'm just trying to say, arrivals after t, we assume that the arrival process is independent of the system, so future arrivals have nothing to do with the current state, and that corresponds to past departures. So amazingly, in steady state, this process is a Poisson process, and the past of this is independent of this state. So that's going to mean that what's come here is going to be this state at this instant. The state at time t is going to depend on the past departures. And the past departures are going to be independent of this. So these two states are independent at the one fixed time in steady state. First of all, in order for this reversibility to work, the whole system has to be in steady state. Secondly, we're only talking about a fixed time in steady state, so that when we talk about the distribution here, it depends on the history of the departures up to that particular time. And that will make this x2 of t independent of x1 of t, because this will depend on these past departures, and these past departures are independent of this, which is astounding and not very believable, but it's due to all this Poisson exponential stuff and reversibility, which is pretty amazing. So that even though this, and I mean, if you change this model and you make all these distributions something else, none of this stuff will be true. But at any rate, in this model, this is a reference case for what really happens in this case. So for other cases, you might do this as an approximation. So in the same way, if you had 7 of these Q's in a row, they'd all be independent in steady state. You'd have the same story. So sitting there in this section 6.6, which is only 4 or 5 pages, are 4 or 5 or 6 theorems, one of which is truncation, and one of which is saying that the departure process from this multi-server queue is Poisson. And the further thing is that if you have 2 of these queues in a row, the second queue is going to be just like the first queue and independent of the first queue. So you can solve all these things. And I guess, gee, this is going to, yes, we should stop soon. This is telling me, I'm getting a message that this is not too superior here. Okay. This is worth knowing in the sense that if you would not want to do this for this problem, right? You do not want to know that. The states here are all pairs JK, where these run over all integers from 0 up. So you don't want to solve this brute force. Whereas the other thing is very easy. So you have these 2 Q's, each of which can be solved separately by as birth death, and that's the answer. Okay, let's advance. So if you have you have a chance to help each other by asking the penetrating question that will clarify all, that all of this veil of nonsense would be removed, and you'd see everything clearly with the right question. There's something here that's so a lot of this in here is to just think about these results there in that 6.6 reversibility. Is very nice stuff to give you powerful, simple story answers for these models. That avoids this. So I guess if you were taking the exam and the problem looked like it was more than 3 or 4 or 5 states, you would think there better not be doing this, right? If it's a big problem, you don't want to do that. I mean, I guess, but in many, many cases, most of these models are birth-death or somehow made out of birth-death, and it kind of all they can be analyzed quite simply. So you don't do that. So anyway, you don't want to just, the theory really pretty much continuous time Markov chains. The theory all revolves around this, and you're just looking for the steady state vector, but the theory is telling you fast ways to get here. Okay, let's advance on the waffles. Okay, let's advance on the waffles, or whatever we're going to get. I guess if you don't go far, if you don't stray far, the odds are very strong, based on my sample, that your choice is predictable. If you stay within the Carlton, right, it's predictable that you can predict what. It seems like you could predict almost what's in the 8 trays there, right? The chicken wings in one and the macaroni in the other, right? And okay, no waffles. Understand the waffles are actually good in John Jay. The waffles are good in John Jay. The problem is not to eat too many. I don't know. Okay, let's advance on the waffles. For those of you who arrived late, remember that a week from Thursday is the second day of reckoning.